All right, class, we're gonna get started. All right, so welcome to Chemical Engineering 2550, Statistics for Chemical Engineers. I hope you're all in the right place. And I guess welcome most of you to your sophomore year. I guess you've been having classes, I suppose, all morning, right? So this is the end of a long day for most of you. Is that right? Okay. All right. This class is officially from 3 till I believe we're 4:20, right? Monday and Wednesday. The typical format of this class is that we will have lectures at the beginning of that period. I don't anticipate that we're going to run until 4:20 every period that we have. But that means that we'll have time at the end for help on homeworks, questions, sort of extra office hours as needed. Also, occasionally, I'd like to bring in videos illustrating different concepts and statistics and that kind of thing. And I think we'll show that after lectures typically. Yeah, I'm not going to keep you here necessarily until the full time every class period. So my name is Tom Zangle. I'll be your instructor this semester. I'll let you know that this is the first time that I'm teaching this class. I'm taking it over from Dr. Silcox, who taught this class for a number of years within the department. So I'll be doing my best to, I don't know, live up to his example as we go through it. My office is in the Sorensen building. Anyone know where that Sorensen SMBB building is? Just up the hill from here. Yeah, I see a few hands. So it's on the 5th floor of the Sorensen building. That 5th floor is actually card access only. So I'll be putting all of you onto the access list to the 5th floor of SMBB so you can actually get to my office. In addition to the time that we're going to have at the end of class periods on Monday and Wednesday as kind of an extra office hours, you can also come by my office anytime. So that's why you'll have that access. Yeah, it's really warm in here, huh? Or you can just make an appointment with me. Send me an email. Email is the best way to get a hold of me. tzangle@chemeng.utah.edu. But we'll run through the rest of the syllabus. So today we're going to go through syllabus material, just introduction to the course, and then we're going to go into the first lecture on probability and statistics. Before we do that, I just want to take a break for a second. I like to start every class by asking if you have any questions. I know we haven't really covered anything yet. I just kind of launched right into it. And I will likely answer a lot of your questions as we go through, about the course, what we'll be doing, what the format of the course is going to be and all that kind of thing. But are there any burning questions before we get started today? Yeah, go ahead.
I think it was something you mentioned.
That's correct. Yeah, we will talk a little bit about that today. I will confess that as I'm teaching this class, so most of my background is in MATLAB. So I'm learning Python a bit as I go through all the course material myself. So I've actually have our 2 TAs for the class, Alyssa and Nathan. They're going to be here on Wednesdays to offer extra help in Python. They're also going to have a help session in Python. Yeah, so they're going to be excellent resources for that as well. Yeah. Yeah. Any other questions before we keep moving? Okay. Okay. So we're going to be using Canvas as the central organizing place for this class, as I suspect many of your classes have been in the past. That means that homework is going to be submitted in Canvas. Homework is going to be done in Python. So homework will be done using Jupyter Notebook in Python. And we will have quizzes, and those quizzes are going to be hard copy that we'll be doing in class. And we'll talk about that in just a second. Okay. So office hours for our TAs are going to be, we decided on Tuesdays. So we're going to have homeworks due on Tuesdays. And so we'll have TA office hours on Tuesdays. But we wanted to decide what time. We didn't decide what time because we wanted to figure out what was going to work for most of the class. So do you all have a sense of what classes or other things you have scheduled on Tuesdays? Is there a good time on Tuesday for the TAs to have office hours? It's all bad, or is there a good time? What are some generally good times for office hours? Anyone? Yeah. Anytime on Tuesday. Yeah. After 2 on Tuesday. Yeah. After 1 on Tuesday. Okay. After 2 sounds like it might work. I will I will ask the TAs to have at least one of the sessions simulcast on Zoom. Yeah, I'll make sure that that's happening. And the other thing is that TAs, Nathan has offered to have an office hour that is dedicated to just installing and using Python, right? Just to make sure that you're all up to speed on the packages and things to get you to use. I'll make sure that he does that on Zoom and records that as well. Okay. All right. So Tuesdays after 2 or so. Does that sound reasonable? Yeah. Okay. Let me make a note. Maybe we'll do like 1 before 2 and 1 after 2, something like that. All right, just sending a note to myself. All right, so we have before 2 and after 2. There are 2 TAs, and we'll likely have 2 office hours. We might try to do something around maybe 1 to 3. Sounds like might be a median time. Okay. So as far as other material, so we will be using Python again in this class, including Jupyter Notebook, right? So all the lectures you may have seen in files on Canvas. I posted the lecture notes for today as a Jupyter Notebook file, as well as just a small set of slides. We'll talk about ChatGPT use, right? Generative AI use. I think you probably heard a lot about it already today. We'll talk about it as regards this class. And all of that is in files, right? So I'll get organized on that and I'll actually put it into a folder in files, but right now it's just sitting in there in files. So that means that you'll need to be able to read and open a Jupyter Notebook in order to access the lecture notes. The way that I'll be doing it is using Visual Studio Code. So that's what you're going to see when we actually get to the lecture part of today's class. We'll be going through cell by cell through Visual Studio Code. There are many other ways to view Jupyter Notebooks, and many other ways to edit Jupyter Notebooks. This one I just find is a nice work environment, and allows you to switch between different sets of basically installed libraries for Python. There are so this is a link to Visual Studio. So suggest you use this, or you can use Anaconda as well. Right, so Anaconda is a distribution of Python that has a number of different interfaces, including Jupyter Notebook, and also will have a lot of the supporting libraries that we need for Python. Does that answer? I know there were some questions, and sorry, I should be asking everybody for their names because I'm going to be learning your names as we go through. There in the back, there was a question in the black hat. You had a question about Python. Does that answer? Yeah, the lectures are built in Python. So there will be Python code in the lectures, and we will be looking at that in the lectures. Yeah. Okay. Great. The suggested text. So there are a huge number of resources for statistics. So there are a huge number of suggested textbooks that you could potentially use for this class. The one that we're going to use most of all is this book, Modern Mathematical Statistics with Applications. Partly just because, I mean, it covers all the material that we need to, but it's also available for free. So if you go to the library website and you just search for Modern Mathematical Statistics with Applications, and then you click on that, you'll get here. If you click there, you'll be able to download the PDF, right? So entirely legally, you can download the PDF for the textbook that we're using in this class. There are a number of other resources, and there will be links to additional readings in the syllabus that cover material that we'll be going over on a particular week, but most of the readings are going to be out of that textbook. And then, again, there are a huge number of resources on Python, and for example, we'll be using, where it's convenient to use Markdown to write text in your Jupyter notebooks and format text within your Jupyter notebooks. So there's, for example, a resource here on syntax in Markdown, and that was used to build the lecture notes if you're looking for an example of that, and should be used as you're putting together your homeworks as well. So as far as grading, I know that's something that we all want to go over. So grading is going to be primarily based on quizzes, and these are going to be in-class quizzes on Wednesdays, about every other Wednesday or so through the semester. And there will be a total of 7 of these quizzes, which you should expect to take about an hour. So actually, yeah, so I've explicitly said 60 minutes, so we should be done by 4 o'clock on those days. So the idea is to make it a little bit lower stakes than having, you know, 1 midterm and 1 final. And they will be a little bit shorter than a typical midterm. And so then 10% of your grading is going to be the homework, which will be submitted as a Jupyter notebook. So all coding should be in Python. We should be able to run the your homework file, right, just to verify that you have all of that done. But as part of that, make sure that you're writing out everything that you're using, right, in your homeworks and on your exams. So one thing I wanted to note here was about ChatGPT. Have you all heard a lot about ChatGPT policies today, I assume? Yeah. No? Did I hear no? Okay. Okay. But you've all heard of it before today, obviously. Yeah, okay. I think for example, for the seniors who just graduated, like their college career was more or less defined by COVID. And I feel like for your class, it's going to be more or less defined by generative AI. I mean, you are the first class to come in and have these tools available to you from the first year. I know not from day one, but enforced from the first year, right? So from the end, right? For those who are going through the traditional program, you've had this from essentially the spring of your freshman year. So I think, and I'll say, as a college, as a profession, as a society, I think we're still trying to figure out what the norms are around this. And so all of this is changing. And so I'll present to you what we're going to do in this class and how we'll handle it in this class, but it will change, right? Because everything has been moving, at least last spring was moving at incredible speed. But I just wanted to talk a little bit about the use of, it is. Yeah. A little bit about how I am thinking about generative AI and how I think you should approach it in this class. And we'll get down to a formal policy on the use of generative AI by the end, okay? One way to think of it is, we have calculators, right? And when calculators first came out, it became, and I'm sure you've heard this analogy before, or maybe you have, when calculators first came out, there was a lot of hand-wringing, especially among engineers, that if everybody's using calculators, they'll forget how to use slide rules, which was true. I don't know how to use a slide rule. I'm sure you don't know how to use a slide rule. Does anyone here know how to use a slide rule? No. So we forgot how to use slide rules, but we learned how to do a lot more, right? Yeah, you get really good at logarithms if you're using a slide rule. And one of the arguments given for, why do you have to learn math, even if you have a calculator, is, well, somebody has to program the calculator. I don't really like that argument because we don't need everyone in society to know how to, program a calculator. But I think the more compelling argument is that you need to know the basics, so you know the limits of the tools that you're using. And so as an example with generative AI, I like to think of it in terms of you need to know how to manage the use of these tools. These tools are uniquely powerful. You need to know how to manage them. So here's a hypothetical example, maybe a strained example. Let's say I need a new roof, right? Let's say that's what my roof looks like. That's not what my roof looks like, but let's say it is. I can find someone who will tell me that they know how to install that roof, right? Like I can go around, I could, post something on KSL, ask for a roofer, go ask around the neighborhood, and I'll find someone who says They know how to install one, probably pretty easily. But like, we could get into some trouble if I don't actually know what a completed roof looks like, right? If I'm trying to manage my roofing project, I'm going to get into trouble. And this is a problem of essentially overconfidence. So, if I do this and my roof gets installed and this is what it looks like, it's not actually my house, it'd be amazing. It might look good in the end, right? And the person who installed my roof told me that the roof was good, and I believe them. But maybe it's missing some flashing at the chimney or something, and I'm going to get leaks and damage down the road. And the basic problem here is that I'm not an effective manager for a roofing project, right? I don't really know how to install a roof, so I can't manage a roofing project, right? I need to rely on people who know what they're doing or people who've had a good experience with these companies in the past. Did this a little bit out of order. So what I'm getting is that you have to be able to detect overconfidence, right? If you're going to be able to effectively manage something or some process or some tool, you have to be able to detect overconfidence. And ChatGPT or these AI tools, they are incredibly confident right now. They are incredibly confident and often overconfident, right? So ChatGPT will act like you can write anything, right? Like an essay or code or crochet patterns or musings on the meanings of life. And this is an example. So sometimes it really can. We'll look at examples of things that it can do, but sometimes, so this was going around last spring, where people were trying to make crochet patterns or use ChatGPT to make crochet patterns. So someone asked ChatGPT, write me instructions to crochet a narwhal. And this is the result when they actually tried to follow those instructions. This is for reference what a real narwhal looks like. They look nothing alike. The thing's cute, but that's not a narwhal. But ChatGPT said it was, right? Because it really has no concept, and it is very, very overconfident. But if you went into it and you didn't know what a narwhal looked like, you might, start selling these things or something, and maybe be embarrassed. I don't know. So you have to understand, and the way to effectively manage what ChatGPT is giving you or these other generative AI tools are giving you is by understanding what's behind it, right? So here's another example. So it can definitely be overconfident. So this came from Bard, which was like Google's ChatGPT clone. And this actually came out of their promotional material. So they put something out asking their generative AI, what new discoveries from James Webb Space Telescope can I tell my 9-year-old about? And Bard very confidently gave this list of bullets, including this one, which was just completely wrong. It was in fact not the first pictures of a planet, of an exoplanet. And this ended up costing Google about $100 million in terms of stock price and valuation. They've since recovered, don't worry, Google's fine. But this, this kind of overconfidence, I don't know, slipped through the engineers at Google. So I want to walk through an example of that kind of overconfidence at work and how you can kind of detect that if you have some idea of what you're looking for. And the example comes from the research that my lab does. So we'll do a little research aside. And this is actually gets to my interest in statistics and my interest in teaching a class on statistics. So my lab measures how cancer cells grow when they're treated with potential therapies. So this top right image or right movie there, those are, that's a movie of breast cancer cells growing and dividing within a dish. And so my lab takes data from hundreds of thousands of individual cells. So each one of those little things you see moving around there is an individual cancer cell. So we measure the growth and behavior of hundreds of thousands of individual cells in a given experiment. And we ask, for example, we treat those cells then with different types of therapies that a cancer patient might receive. And then we ask which therapies are effective at limiting the growth of those cancer cells. And one of the questions that we've been looking at lately is, can we identify resistant populations of cancer cells that are still growing even when exposed to drugs? So this is real data that comes from a patient sample. So cells that came from a breast cancer patient who was treated Here at Huntsman, the cells that are not treated with a drug are shown in these blue distributions here. So these are distributions of growth rates of cancer cells. And then the pink distribution, that shows cells that have been treated with the drug, and we're measuring the growth rates of those cells over time, is shown here. And it looks like, if you squint, kind of, that there might be two populations of cells here. As in one population that's still growing, even though it's treated with this drug, and one population that's dying, which is the thing that we want. And so a question that my lab has been trying to address is, can we identify resistant populations of cells within this? Like, aside from just squinting at it and saying it looks like there's two, right? Can we make some statement with some statistical confidence, right? So can we make some statistically validated statement about whether or not there are two populations here? And we'll talk a lot more about these kinds of tests later in the class, but just to get started, I tried to use ChatGPT to do a test case where we put in, I asked it to make up essentially some data with some specified distribution and try to curve fit that. So I asked it to write some code. I said, write Python code to generate random noise that is from two normal distributions of different means of standard deviations, then fit that random noise with a 2 Gaussian model, right? And this was the output. And I should note this is ChatGPT v3, right? So not the latest one, v4, and from last February. I've heard that ChatGPT may have gotten worse at coding since then, so beware. But this is the output, just the straight up output from ChatGPT. And this looks like Python code. And if we run it, it is in fact Python code. This is executable Python code that ChatGPT gave me just like straight out the box, right? And this looks more or less like what I would expect. But I was asking it to basically generate these distributions and then do a curve fit to these distributions, right? So this looks correct. But if we look carefully at it, all it's really doing is plotting the things that it's not actually doing a curve fit. It's plotting, it's showing a curve, but it's not showing a curve that is a result of a curve fitting operation, right? It's as if you generated data according to y is equal to mx plus b, and then you plotted the line of y is equal to mx plus b instead of doing a linear fit and trying to see if you got the actual right slope out, right? So it's actually just plotting the thing that it input in there, but actually didn't get the question correct, right? It says it did, right? It's overconfident. It's not going to tell me that it didn't do the thing I asked, right? The only way to figure out that it didn't do the thing I asked is by understanding what I'm really actually looking for, going in, reviewing the code, and then realizing that there was a mistake, right? There's no fit here. There's no curve fit here, right? That's really the key. So I asked it again, right? Because with these tools, you can go in and you can iterate back and forth. And so I said, make the fitting use least squares nonlinear fitting to a 2 Gaussian model. We'll talk a little bit about curve fitting later in the class. And it gave me more code. And the key here is that now there's this line down here that includes curve fit. So now it's actually doing it. And this works, right? So if you run this now, this actually works. And then now I have code, right, where I can go in and evaluate, change all these parameters and evaluate it and do all kinds of testing, right? So the point I'm trying to make here is that this will likely change the way you work, right? This is going to change the way we all work. This has already changed the way that I work. It's probably for the better. This is a really powerful tool. But you have to know how to check the result and manage what's going on, right? So even though in this class, you're going to be doing a lot of Python code, we're going to be using Python code to teach the class. You're going to be using Python code in your homeworks. Your quizzes will be a lot more conceptual, about concepts, and we'll be doing things on pen and paper. But you might ask, when you're done with this class, if you can get this out of ChatGPT, why do you need this class? And the answer is so that you know how to manage the AI, so you know what results actually to expect from it. Does that make sense? So as far as a policy is concerned, in this class, first, as I said, the quizzes are going to be in person and closed book. So that means that you're not going to be online. So generative AI, any other kind of online resources cannot be used for the quizzes. So the quizzes are going to be all handwritten. On the homework, however, right, you're going to be doing the homework in Jupyter Notebook. You're going to be doing the homework in Python code. I can't lock down ChatGPT to all of you on the homework, and I'm not going to try. Policy here is that generative AI tools like ChatGPT and all this can be used, but they must be cited. And this is the taking a cue from Dr. Butterfield. This is how I would like them to be cited on the homework, right? So you state what the prompt was, state what tool you used, what version it was, who made it, date produced, and a link. Okay, that makes sense. So here's an example. So this comes from actually Dr. Butterfield. This is a prompt that he sent to Midjourney for an illustration of Stokes flow around a sphere. Got this crazy looking image with all of that information populated on it. Okay, does that make sense? Does this jive generally with policies or any other discussions you've seen in other classes for use of this? No? Yes? No? No. Okay, well, this is what we're going to be using in this class. Okay. Any questions or comments? Have you all played with this so far, this ChatGPT thing? I mean, I feel like you should. Yeah. So yeah, just go to OpenAI, chatgpt.openai.com. You can make an account and start playing around with these tools, which are pretty powerful. Okay. So as I mentioned, the quizzes are going to be closed book, closed notes in class. So we're going to be avoiding any use of ChatGPT on those. Yep. Yeah. I'm going to amend the second statement to be 60. Yeah. Yeah. Apologies. Yeah. If you notice any other errors in here, please let me know. And down below, this is the schedule for what we're going to be covering in class, right? So today, today and Wednesday, we'll be talking about Intro to Probability and Statistics. And here I mentioned that we would have readings listed, and these readings, when given as a chapter number, these are coming from that DeVore book. All right, any questions on class admin or anything before we move on? Aside from how do we get air conditioning working in this room? Because I feel like it's hot. All right, then we're going to go into our first bit of material, which is going to be in Jupyter Notebook. Was anyone able to download the file ahead of time to follow along? Yeah. If you weren't and you have a computer, it is up in files. So if you look at it here, the Python notebook is available in files on Canvas. All right. So we're going to start this class by talking about, I need to figure out how to turn this off of dark mode because I feel like that's a lot harder to see on the screen. Give me 1 second. Nope, I'll figure it out for next time. Okay. We're going to leave it there for now. So today we're going to start talking about probability, and we're going to start walking our way through concepts that we need to understand some questions in probability. I should note that many of the books that we recommend or that are recommended for this class and actually many classes that cover similar material to what we're going to cover here are actually called probability and statistics rather than just statistics. And the reason is that whenever we're making a statement that we have justified using statistics, it is inherently a probabilistic statement. So inherently, when we say, like, for example, if my lab is trying to say that there are two distributions, there is a resistant population of cancer cells within the treated population data that we have, we will assign a probability to that. We will be using statistics to assign a probability to that statement. Right? We'll say that maybe we can detect two populations are resistant, and then a sensitive population with a probability of 95% or something. That would be nice. So inherently, whenever we're making a statistical statement, there will be a probability associated. And so in order to understand statistics and get into statistics, we have to first talk about probability, right? So we can understand the outcomes that we're going to get from statistics. So we're going to start with, so many of these lectures are going to start with an example, right? An example kind of problem that we're trying to approach. And we'll talk through the concepts and definitions that we need to know in order to get to that concept. So the concept here is going to be, so shown here, cancer on my block. So suppose that there are 120 people on your block, and last year 6 of them were diagnosed with cancer, right? That seems like an awfully high incidence. So should you move, right, from your block? Like, is there something going on there that you should be getting away from? And this is based on information from this book by John Hart. So we're going to need some different data to solve this problem. So this is, let's start with, we're going to use data from 2016. So we had 1.7 times 10 to the 6 people in the United States were diagnosed with cancer, and the population was 3.2 times 10 to the 8th. And so we're going to try to answer the question of what the probability of finding a cluster of 6 cancers in a block of 120 is, right? And so we're going to ask things about, like, how many of such blocks are there in the United States, and we'll get through to some of these definitions and probability, right? And just to see how out there is the idea that we might have 6 cancer cases on a block of 120 people. But before we get there, we have a number of definitions that we have to get through, right? So we're going to start with probability. So probability, it says here, is a study of randomness and uncertainty and helps provide a foundation for statistics. Can you all read this, or is this impossible to read? Is this better? Yeah, much better. Okay, great. Apologies as I get through. Yeah, I have never taught in a Jupyter Notebook environment. I'm sure. Have you all had a class in a Jupyter Notebook before? You have? Okay. I've never taught from a Jupyter Notebook before, so this is new for me. Maybe not for all of you. All right. So probability is a study of randomness and uncertainty, and provides a foundation for statistics, right? So as I said, any statistical statement that we make is going to be inherently probabilistic. And when we say that we have when we're talking about the probability of an outcome, then we would properly define that as the proportion of times that random event would occur if we observed it infinitely many times, right? So if I'm flipping a coin, right, the probability of getting heads is 50%, but if I flip a coin 100 times, the likelihood that I have exactly 50 heads is actually very low, right? So, but that brings us to the law of large numbers, which says that the proportion of events, we call it p hat sub n, with a particular occurrence or a particular outcome approaches the probability of that outcome as more data are collected. Right? So if we come back to flipping a coin, if I flip that coin 100 times, I'm not terribly likely to have exactly 50% heads, right? Even though we know the probability of getting heads is actually 50%. But if I flip that coin 1,000,000 times, right, 100 million times, then my actual number of occurrences of heads is going to approach 50%. Another definition we need is about disjoint or mutually exclusive events. So we would say that two outcomes are disjoint or mutually exclusive if they cannot both occur. So an example here would be rolling a 6 with a die and a 3 with that same die. They are mutually exclusive in a single roll, right? So, or another example from the coin flipping, I cannot flip the coin and get both the heads and the tails at the same time, right? So those two events are mutually exclusive. I can flip the coin twice and get a heads and then a tails, but on the same flip, I cannot get both. So those would be disjoint or mutually exclusive events. So this leads to the addition rule for disjoint outcomes. So let's say we have A1 and A2, and they are two disjoint outcomes. They are two mutually exclusive outcomes. They cannot occur at the same time, right? Like I cannot get both heads and tails on the same coin flip. So then the probability that either A1 or A2 occurs, we'll sometimes write it as probability of A1 union A2. So we'll see that symbol, that big U. Whenever I see this, I automatically interpret it as logical OR because I'm more comfortable with programming language, and so that's another way to think of it. So probability of A1 or A2 is just the sum of the probabilities of A1 and A2, if they are mutually exclusive, if they are disjoint events, right? So if A1 is probability of heads, if A1 is heads, A2 is tails. So the probability that I get either heads or tails on a coin flip, right? Probability that one of those two things happens is probability of heads, 50%, plus probability of tails, 50%. So this is just telling me that something's going to happen, right? I'm going to get heads or tails. If there are many disjoint outcomes, right? So if we're talking about a die roll instead, right? And let's say we have 6 faces, so A1 through AK, where K is 6. Then the probability that one of them will occur would be just the sum of those probabilities. Okay, if they're disjoint, if they're mutually exclusive, they cannot happen at the same time. But not all outcomes are necessarily disjoint, right? So we may have some set of outcomes that can happen at the same time. And so if A and B are two outcomes that may or may not be disjoint, then this probability of A or B becomes modified. So we end up with probability of A plus probability of B minus the probability of A and B, minus the probability that two things occur. Basically, we take the probability of those individual events, A and B, and we subtract the overcounting that we were doing because they can sometimes occur at the same time. So this probability A and B, we can write it here, probability of A intersection B, that upside down U, we can read as intersection, or you can translate it back into a logical AND. This is the probability that both events occur. So if we look at a single die roll, and A is the roll of an even number, and B is the roll of a number divisible by 3, right? So now those two events are no longer disjoint, right? So I can have both an even number from my single die roll, and I can have that number potentially be divisible by 3, right? So I could roll a 6, which is both even and divisible by 3. So this tells me, in this example, the members of A are 2, 4, and 6, right? Those are the even numbers that I can get out of my die roll. And the members of B are 3 and 6, right? That makes sense? Okay. So 6 is in part of both A and B. So these events are not disjoint, right? These outcomes are not disjoint. And so to find the probability that I get either something in set A or something in set B, I would have the probability of A plus the probability of B minus the probability that I'm in both, right? So I have to subtract that overcounting. That makes sense? So this is 3/6 plus 2/6 minus 1/6. So I actually end up with 2/3. Okay. All right, there's gonna be a lot of math, more or less a math class. I will try to figure out how to get the air conditioning going because a math class in a very warm classroom is probably not the best thing late in the afternoon on a long day, but we're gonna press forward. Okay, so another definition is complement. So the complement of an event A, we're going to write as A prime, and it represents all the outcomes that are not in A, right? So in our coin flip example, if heads is A, then tails is A prime, right? In our die example, if A is the probability that we get an even roll, then A prime would be, or sorry, if A is an even roll, then A prime would be an odd roll. Right? So then the relationship between A and A prime is that the sum of A plus A prime is equal to 1. Right? So the probability of all possible events, of any of all possible events occurring is going to end up as 1. So this means we can also write that probability of A is 1 minus the probability of A prime. So 1 minus the complement gives us the probability of an event. And we'll see this can often be like a back end way of getting to the probability of the event that you really want to know about. In some cases, it may be a lot easier to write out probability of A prime. Let's say you're interested in probability of A. In some cases, it may actually be a lot easier to figure out the probability of A prime. And so having that tool can actually be pretty useful. All right, moving on through. So to independence. So we'll say that two outcomes are independent or uncorrelated. So not related to one another, not directly dependent on one another. If the occurrence of one event has no bearing on the outcome of the other. So we would say that two consecutive tosses of a coin are uncorrelated or they're independent, because whether or not, if I get a heads on the first flip, that has no bearing on whether I get a heads or a tail on the next flip. So the probability that two such events, A and B, right, that are uncorrelated or independent occur is just going to be the probability of A times the probability of B. Right, so the probability of getting two consecutive heads on coin flips would be 0.5 times 0.5, right, or 0.25. The probability that K independent events all occur, right? So if I do K coin flips and I want to ask what's the probability that I get K heads in a row, it would just be multiplication of all those probabilities together. Okay. Next one will be multiplicity. So now we're going to talk about combining the number of possible ways that I can get different outcomes. So if I have now sets A, B, and C that each have a number of different elements, then the total number of ways that the possible outcomes can occur is just going to be the multiplication of all of those different numbers, right? So if there are, if there are 10 ways of, choosing the color of something, 20 ways of choosing the, the flavor of something, and 2 ways of choosing, let's say we're talking about ice cream, 2 ways of choosing the way that we can serve it, and those things are truly independent of one another, then the number of possible outcomes is just going to be multiplying all of those things together. All right, so it'll be the multiplicity. However, oftentimes when we're talking about a number of events that we have to consider, we're interested not just in the number of or the multiplicity of possible outcomes that we can have, but in the way those outcomes are ordered. And so, or in the way those outcomes are arranged. And so we define that using the permutations. And we would say that the number of permutations of R objects, or ways of arranging R objects from n distinct objects. So we write this as NPR, right? Is written as, so we can write it as n times n minus 1 times n minus 2, all the way out to n minus r plus 1. And if we evaluate that using the factorial notation, what we end up with is n factorial over n minus r factorial, where this is the definition of factorial. Have you all seen definition of factorial previously? No. Okay. Apologize, some of this early stuff is a little dry. We'll get back to our example in just a few minutes. So this would be the number of permutations of a number of arrangements. So if we have, 10 different, hats, and we're choosing a set, and we're choosing some arrangement of, 3 hats or something from that set of 10 hats, then this would give us the number of possible permutations, right? It'd be 10 factorial over 7 factorial would give us the number of ways of arranging those. We also will often talk about combinations, right? So as distinct from permutations. So this would be the number of ways that R objects can be selected from n distinct objects. So now we're going to say that so the permutations would be like if we were choosing from those 10 hats, but we're allowing them to go back in, right? We're allowing, if we choose one hat out of that pile of 10, we're allowing it to go back in that pile and possibly be collected again. So more properly, most of the time, we're going to be interested in number of combinations where we're selecting without replacement. So we're pulling a hat out of the pile, but we're not going to put it back in. And so this would be the number of ways that R objects can be selected from n distinct objects is the number of combinations. So this is really just the number of permutations over R factorial. And so we're going to end up with n factorial over R factorial times n minus R factorial. All right, still with me? Maybe? I get some sign of life. What's that? That's a good question. Are there less combinations than there are permutations? Mathematically, yes. Why would that make sense? You're not replacing it, so there are going to be fewer combinations, right? So exactly. So with combinations, we're not replacing it. It's like we have this row of 10 hats sitting here in front of the room, and as I select it, I'm putting it over there in that pile, right? It's a number of possible combinations I can make by putting it over in the pile. Permutations would be I pull one out, right? I pull out the red hat, and then I put the red hat back, and it's allowed to be selected again. That makes sense? All right. Any other questions? Okay. All right. We're almost going to get back to our example. Almost going to get back to our motivating example. And I think shortly after that, I'm going to let you go for the day, for the first day. Another concept here is a random variable. So we define a random variable as the outcome of some experiment. So actually, so I have a stats textbook from grad school called Random Data. I feel like every time somebody sees this book sitting on my bookshelf, it says Random Data, I get a comment like, oh, isn't that just meaningless, right? If it's random data, isn't that just meaningless? Right? They're surprised that it's actually a pretty thick textbook. But what it's really talking about is random variables and how we can deal with results from real experiments. Real experiments have noise that has some random component to it. And when we have such data, we call it a random variable. So even though there may be some piece of it that is deterministic, or some piece of it that we're trying to maybe is our measurable signal, we still call it a random variable, right? Because it has noise. It's real. It's the outcome of some real experiment. So the weight and height of a randomly selected professor would be random variables, right? And we often write these random variables in capital letters, like here I'm saying X and Y, that's capital X and Y. The possible values would often be written in lowercase x, lowercase y. These random variables are going to come in two flavors, discrete and continuous. The discrete probability distribution gives precise values of X and their probabilities, right? So if I have, can somebody give me an example of a discrete random variable? So what would be a discrete random variable? Yeah.
Number of fingers lost in
Number of fingers lost in a horrific accident. That would be a random variable. Hopefully the number is 0. Occasionally it may not be. Great. And a continuous variable would be something like height, right? So height we tend to measure continuously. If I bin that height into 1-inch bins, then it would become a discrete variable, right? But if I'm allowing it to have a number of decimal places, then it's a continuous random variable. So this discrete probability distribution must always be positive. So this f of x, so the probability of obtaining a value of our variable equal to lowercase x is always going to be greater than 0. So if we look at the probability distribution for a dice roll, right, something that's a little bit more even than hopefully the probability of losing digits in an accident, the probability of each one of those faces coming up is going to be 1/6, right? So each one of those probabilities, f of 1 is equal to 1/6, f of 2 is 1/6, and so on. And the sum of all those probabilities, right, the sum of all f of x is equal to 1, right? So for the dice roll example, if I have those 6 possibilities, the sum of 1/6 plus 1/6 plus 1/6 plus 1/6, right, 6 times is equal to 1. And in when we get back to the cancer question that we started this piece of lecture with, we're going to be using what's called the discrete binomial distribution to help answer this question. Before we do that, one more definition before we get back to this is that if we have a continuous, just a note about continuous probability distributions. So if x takes on a continuous value in some, it can be a finite or an infinite range, then the probability that we get exactly any one answer, any one number, is actually going to be 0. So the probability that we have that we get exactly some number as the outcome of our trial actually goes all the way to 0. But what we'll often do is look at some infinitesimal interval where we look at not the probability that we get exactly, some professor's height that is, 5 foot 8.250 inches, but we look at the probability that we have, that measurement within, say, a quarter of an inch or something. So we often call the continuous probability density function the frequency function. So it's the frequency that we get a particular value. And in analogy to that discrete probability function, the integral over our entire range, if it's infinite, it would be from minus infinity to plus infinity. If it's over some finite range, it'd be over that finite range. The probability, the integral has to be equal to 1. So with this, we're finally ready to come back to our example from about cancer. Any questions about, we went through a lot of definitions, I know. Any questions about the definitions that we've gone through so far? Okay, so we'll be applying some of these now as we go through this example. All right, so let's get back to this example. So let's say we have 120 people living on your block. Last year, 6 of them were diagnosed with cancer. You're wondering whether or not you should move, right? This is concerning. This seems like it's a really high number. So should you actually move? Bren, we're going to be addressing this by trying to figure out like what really is the probability of this kind of an event happening, and that'll give us a sense of, is this something truly outlandish? So we're going to start by defining the population within the country, and the number of cancer diagnoses within the country in a given year, right? So here we're just using 2016 as an example. So that'll define basically the number of cancer cases that we expect within a given group. We have the number of residents in the block, the number of residents on your block diagnosed with cancer, right? 120 and 6. And so then the probability of any particular person, right? Assuming that a cancer diagnosis is independent and randomly distributed, evenly distributed in the population, at least to start with, that probability would be the number of diagnoses, right, within that given year divided by the population, right? So 1.7 times 10 to the 6, 1.7 million over 320 million. And so the that probability P, 0.005, right? So that's the number of cases per capita in a given year. And then the mean number of cancer cases that you would expect on a given block of 120 people would be just, right, again, if we assume that these events are independent. So we're going to just sum up those number, right? Sum up the probabilities that any individual person on the block is diagnosed with cancer in a given year. And so we can find that as the this probability for one individual times the number of residents on the block, right? Does that make sense? We're just going to add up all of those because we assume they're independent. And then we have this number of residents times P. So the mean number of cancer cases per block, we're going to have this 0.6375 average number of cancer cases per block of 120. So that's obviously less than 6, right? So we might be worried because that number 0.6 is a lot less than 6, what we actually observed in that past year. But we want to start assigning a probability. We want to get a little bit more rigorous with our definition of the probability that we actually see 6 cancer cases on the block. So the next thing we might do is look at, well, what's the probability that we have that a given 6 people on the block are diagnosed with cancer in a given year? And so the probability that a given 6 people on the block are diagnosed with cancer in a given year is just that P raised to the power of the number of cases that we saw. And so if we look at that outcome, we get this 2.2 times 10 to the minus 14. So again, the probability that any given 6 people on the block have cancer in a given year is something infinitesimally small. So we might start to be a little bit worried here, right? Because that number makes it seem like that 6 that we observed is really actually incredibly bad. In order to figure out, but one thing that we're not taking into account when we have that probability of 2.25 times 10 to the minus 14, we said that's a probability of a certain 6 people having cancer within a given year. If we want to find the probability that exactly 6 people on the block have cancer in a given year, we also need to account for the other 114 on the block. So first we have to find the probability of the complement. So the probability that the other 114 people do not have cancer. Right? We're trying to find the probability that exactly a certain 6 people are diagnosed. So we need to find the probability that the other 114 are not within that given year. So this is going to be the complement of P, 1 minus P, and it then raised to that 114. Res minus res C is going to be 114. And so the probability that a given selection of 114 people are not diagnosed in a given year is 0.545, pretty high. So then our revised probability that we see 6 people exactly with are diagnosed with cancer in a given year, and the other 114 are not, is 1 times 10 to the minus 14. So still very, very low, right? In fact, slightly lower, because we're now accounting for those other 114 people not being diagnosed in a given year. But the thing that I hope I've been trying to emphasize here is that this number that we've been computing is for 6 particular people. So we've been asking the question of, what is the probability that 6 particular people on the block are diagnosed in a given year? But we could have any 6 out of 120, right? It could be any set of 6. So we have to multiply by the number of groupings of 6 that we could take out of that population. So we're going to use within SciPy, right? So we're going to use the com function in order to do this. And now we're going to end up with the number of combinations of people on the block, where we're choosing 6 out of 120, right? So the combinations of, again, 6 out of 120 is going to be 3.6 million, right? Possible combinations of 6 people out of 120. And so that now the probability that we actually have 6 cancer cases diagnosed in 1 year is that probability that we found up here, we call PQ, times the number of combinations that we found. And so we end up with this number, 4.4 times 10 to the minus 5. This is still pretty low, right? So this number is still pretty low, and we might expect that 6 cases is still an outlier. And just as an aside here, we mentioned the binomial distribution. This is actually exactly what the binomial distribution is calculating. So the binomial distribution, so we can again find it in SciPy by importing binom. And then this binomial distribution basically allows us to input the number of that we're trying to choose, the number of items that we're trying to choose out of the population that we're trying to choose it from, times the probability that any one of those events occurs, right? So just by putting in res C, res, and P, then we end up with the same number that we just computed, right? So binomial distribution is basically telling us the probability that we have a certain combination of events out of a given population when we have the specified probability. Okay, so we can go through all of this using our definitions of essentially probabilities, combinations, or we can use the binomial distribution as kind of a shortcut to get to the same result. And so the conclusion that we're going to reach is that probability of 6 cancers on a block of 120 people is very small. And so you may in fact be concerned. The next piece of this is how many such blocks might exist in the United States. So do we expect to see such an event happen at all within the United States? And we're going to get into that, I believe, in the next class. So we'll also see that this binom PMF gives the same answer as our calculation. And so we're going to start off next class by first explaining what the binomial distribution is in a little bit more detail, aside from just being a shortcut to the calculation that we just went through. And then we're going to go through the rest of this example. Okay. All right. Any questions before I let you all go for today? Yeah. No, I mean, if we assume that the events are independent, then the probability that like the next person comes down with cancer is independent of the fact that there were 6 there already. That's kind of gambler's fallacy, but we'll talk about that another time.